All right, everybody, this is day number 5 on rotational volumes, disk, washer, and shell method. Okay, so I just want to quick talk about how we would find the volume of a cylinder, right? So how would we find the volume of the cylinder? Well, we'd need to know R. So that would assist us in finding the area of the base of this solid. So I would take pi r squared, that would give me that area. And then we'd multiply it by the height which would be this length. So in this case, let's say we took the line, I don't know, y equals 2, and we revolved it around the x-axis. We revolved it, let's say from 0 to, I don't know, 3, right? Well, we could just use the fact that we know that 2 is our radius, right? And then we could go ahead and find our height, which in this case would be 3. And we could calculate it using our geometry skills, or we could actually integrate this. And the way that we'd integrate this is on the same limits, right, from 0 to 3 of pi r squared, and our h is actually dx, right? The dx is what takes us from 0 to 3. So what is r? We need to talk about r for a moment. R is actually going to be an output of a function. In this case, the output of our function is always 2. But basically what we're going to do, this is called the disk method, right, because we're inserting circles, right, of width dx. Therefore, we'd take pi times whatever our f of x value is. And it could change, right, if the function isn't just a horizontal line like this one. And we integrate such, okay, on the interval that's given. So let's just go ahead and find the volume using this integration method here. That'd be pi times the integral from 0 to 3 of f of x. Well, what's the integral of 2? Well, it'd be 2x, right? So it'd be 2x from 0 to 3. Now, I did forget something. What did I forget? I forgot to square 2, right? This would be 2. F of x is always 2. So it'd actually be 4x from 0 to 3. Okay, so let's do a little evaluation here. This would be pi times 4 times 3, which is 12. Okay, minus 4 times 0, which would be 0, so it would be 12 pi. 12 pi whatever, units cubed. Now let's go back for a second and let's look at what this would actually be using geometry. So our volume would be pi times r squared, which is 2 squared, times the height, which was 3. 2 squared is 4, 4 times 3 is, look at that, 12 pi units cubed. All right, so this is our general form right here. We are going to use this when we do disk method. Okay, we're going to take f of x, square it, take the integral from whatever our limits are, times pi. All right, let's do an example. One arc of sine x is revolved 360 degrees through the x-axis, using the identity that sine squared x equals 1/2 minus 1/2 cosine 2x. Find that volume of revolution. So we're going to go from 0 to pi of pi times r squared. R in this case is sine x squared dx. Now it's telling us to use this identity because that's not easy to integrate unless you can reduce the power to this 1/2 minus 1/2 cosine 2x. That actually comes directly from the double angle identity. So why don't you go ahead and try to integrate that. Okay, so I've got my integral here. I can go ahead and evaluate. This is pi times, let's insert pi first, that'd be pi over 2 minus 1/4 of sine of pi over 2. Alright, and minus, let's insert 0. That's actually going to be really easy because 0 over 2 is 0, and sine of 0 is also 0. So that'll be relatively easy there. So I'm going to take pi, and I'm going to multiply it by pi over 2 minus, what was it? Oh boy. What's the sine of pi over 2? Well, it's 1. So it would be minus 1/4. So to me, let's see here, I get pi squared over 2 minus pi over 4. And I would probably, I don't know, that's a good form. That would be the area that revolved. It's a pretty good form. I guess there'd be other alternate forms. But that would be the volume of sine of x from 0 to pi revolved around the x-axis using the disk method. Okay, what I'd like to do now is kind of identify how we would find the volume of a cylinder with a hole in it, kind of that toilet paper looking situation. Well, before what we did, let's say that let's say we got a situation like this, right? Before we said we'll take f of x, square it, right? So this was, if we didn't have a hole in it, we went from, let's say, I don't know, 0 to 4 pi times the function f of x squared dx. Well, now what happens when I take out an inner function? Oops, I want a different color there. Well, now I'm basically, what I'm doing is I've got this outer function, I've got this inner function, and I've got this new space, right? Now the distance between, or the radius of that is no longer just f of x, right? Do you recall this for finding the area of the annulus? Pi big R squared minus pi little r squared. That's what we're going to do here. So let's say that green is g of x and blue is f of x. What I want to do here, in order to find the volume of revolution in this case, is I'm going to go from 0 to 4. I'm going to pull the pi out of this, right? Pi big R squared minus pi little r squared. I'm going to pull the pi out, which means I have big R squared minus little r squared. Big R in this case is going to be f, little r in this case is going to be g. It'll always be your higher function minus your lower function. So how would I do the integral here? Well, I would take individually f of x squared minus g of x squared dx. That is the washer method. Okay, I'm slipping washers in there. Now, just an FYI, I don't think we do any shell method in today's notes. But a shell method, all that is taking two functions. Let's say we've got f and we've got, g. And if we were to revolve those this way, right, we would get something that looks kind of like this. Right? So we would get this solid like that. Right, that is called the shell method. All right, it's the same thing as the washer method, just in a different dimension, right? Just going the opposite way. So let's apply this to this situation. Find the volume of revolution generated by revolving the region between y equals x squared and y equals square root of x about the x-axis. So let me see if I can help you visualize this. right? I'm taking this function, square root of x, and this function, x squared, and I'm revolving them to create this solid. Okay, now that doesn't look like a solid there, but it will here. Now you can imagine that I'm creating this solid whose width is changing, right? Because the distance between those two functions is always changing. So let's go ahead and erase this. And let's figure out what big R would be and what little r would be. Well, big R in this case would be any y value here. So to find this volume of revolution from 0 to the 0.11, of course I'm going to this one, right, would be pi big R squared. Well, big R is square root of x squared minus little r squared, which is, in this case, x squared squared. So that'll turn that into x to the 4th. Alright, so I'll have pi times the integral from 0 to 1 of x minus x to the 4th dx. Alright, pretty easy to integrate. That'd be pi times, what would that be? X squared over 2 minus x to the 5th over 5. Thank you for using nice numbers like 0 to 1. So if I plug in a 1, I will get 1/2 minus 1/5 minus, if I plug in a 0, clearly I'll get 0 minus 0. And now I can find that volume. That'll be pi times whatever 1/2 minus 1/5 would be. Well, that'd be 5/10 minus 2/10, which would be 3 pi over 10 units cubed. Perfect. All right, let's move on. Oh my God. All right, so here we are. I want to do an example using the disk and the washer method. So first of all, let's find the coordinates of A. So the coordinates of A would be where e to the x over 2 equals e to the 1. So that'd be where x over 2 equals 1, which would be at x equals 2. Okay, so I know that point right there is x equals 2. That'll be helpful. So let's find the rotational volume. It looks like around the x-axis. Okay, so I'm going to employ this again, where big R is my greater function and little r is my smaller function. It looks like in this case y equals e is my larger function for that interval, and y equals e to the x over 2 would be my smaller function. So for part B, I would take the integral from 0 to 2 of pi times big R, which is e squared, minus the smaller function, which is e to the x over 2 quantity squared dx. Okay, so I get this integral right here, which would be evaluating the following from 0 to 2. Okay, let's integrate. This would be e squared x minus e to the x from 0 to 2. All right, let's do a quick work on this, simplifying that. If I plugged in a 2, okay, if I plugged in the 2, I'd get 2e squared minus e squared, which will be just e squared. If I plug in a 0, I'll get 0 minus 1. So the answer to this would be pi times the quantity e squared plus 1. If you left your answer as pi e squared plus pi, that would also be sufficient. Okay, part C, volume of revolution around the line y equals E. Okay, now this is not going to be a washer. This is actually going to be a disk. So imagine you get this solid, right, by revolving the green function around that red line. Okay, so then how do we come up with the radius here? Well, the radius is just going to be all of these distances, right? Each of these. Okay, and those values are all E minus whatever e to the x over 2 is. Okay, so same limits of integration. The volume of this disk would be from 0 to 2 of e minus e to the x over 2 squared dx. Recall, we're doing the disk method, right? This is f of x squared dx, right? F of x is this new thing, right? This new value here. Okay, this is not washer method. Not washer method, this is disk method. Okay, let's keep moving. I believe at this point this problem becomes a calculator problem. Yeah, I believe it does, although we could probably go through that mess. Let's go ahead and just use the calculator for this. Okay, so with the calculator, what I would do is I would type this in for y1, and then just use your TI-84, whatever you got on hand, and do the following. All right, and come out with an answer. I'll come back with mine. Okay, so just so you're aware, the shortcut for this is Math 9. That'll get you numerical integrals. It'll give you some nice stuff to fill in here. Of course, you just fill it in appropriately. Math 8 would give you numerical derivatives at some value for x. Sorry, I totally jacked that up. Okay, so my value here, don't forget to multiply by pi, would be 7.803 units cubed. Okay, I want to go back to the beginning here for a moment. I'll probably just, if I can, I'll erase some of this. And I can, that's great. Okay, I want to jump into part D. And then I want to look at some horizontal rotations, which we would do about the y-axis. So let's say I want to revolve this around the line y equals -2, right? So now it's not the x-axis. I've added a little bit to it. I want to revolve it around that. Now my upper function would still be e. My lower function would be e to the x over 2. But then I want to add in this gap here, right? So I would take the integral from 0 to 2, no change there. When I look at f of x, or my upper function, I would take this, and I'm adding 2 to that, right? I'm adding 2 to that distance, right, to that radius. So I'm adding 2. I'm really subtracting that -2 and then squaring it, but in essence, what I'm doing is I'm adding 2 to that, okay? And then my lower function, e to the x over 2, I'm subtracting -2 from that as well, right? And that'll find me these lengths. Oops, I'm sorry. So e plus 2 will give me that length. E to the x plus 2 will give me that length, not perfectly. How about that length? There we go. At any given value. All right, and so then I'm just going to add 2 to that, square that, and boom, we go. Okay? All right. That would yield us, using Math 9, some value. Let's see what we get. What I would do is put this in as y1 and put this in as y2 and use Math 9 and go for it. All right, don't forget to multiply by pi. Oops. So that volume of revolution would be 51.488 units cubed. All right, I believe that is it for this slide. All right, so in this example here, what I want to do is I want to take and I want to revolve a function around the y-axis. Okay, so there's not a whole lot different. We're just going to change our variable of integration. So this function x equals y squared, actually if you were to look at this, this would actually be y equals plus or minus the square root of x. Okay, with the positive portion right here and the negative portion down here. So since we're revolving this about this line y equals 1, excuse me, about the y-axis between y equals 1 and y equals 2, we can just ignore this piece altogether. Okay, so there's only one function involved. It's rotating about the y-axis. So there's going to be a solid formed, and that solid is going to kind of take this shape, right? So not well sketched, but it's going to take on this shape, right, as it revolves around the y-axis. So it's going to kind of do this going around the y-axis. Okay, so now instead of in terms of x, we want our integral in terms of y. So I would take pi times the integral from 1 to 2. Now it's in terms of y, right, because I needed these 2 points of intersection. Well, this first one would be 1, 1. The second one would be 4, 2. Okay, so I'm going to do that. My function is y squared. I'm going to square that dy. So now I just do a little bit of work on that. That'd be pi times y to the, this would actually be y to the 4th, so that'd be y to the 5th over 5 from 1 to 2. Alright, so let's do a little evaluating here. That would be 2 to the 5th, which is 32 fifths, minus 1 to the 5th, which is 1 over 5.